Anatomy of search engine. In this lecture, I will cover design criteria of search engines, architecture, and basic data structures used in development of search engines. So this is the simple demonstration, simple picture that describes how search engine works. Suppose your user types some keywords and searches. Then how it works? It first uses add indexes for added results, for add support results, and general index for search results. And how these indexes came? First, their search engines web crawlers crawls the web pages, and then the indexes prepare the indexes and rank them also and store them. And now after that, based on the user query requirement, the pages are retrieved. So this is the simplest structure of web search engine. So the role of crawler, indexer are very important. So the first step is the crawling the web. I use one figure to represent that. From internet resources, web crawlers finds and fetches the web pages, and indexers sort and create indexes of the words in the database. So this is the Google database, and after that a query processor technique is used. When we apply query through search engine, then query processor responds with particular answer. Google has a fast distributed crawling system. Each crawler gives roughly around 300 connections open at once. Google can crawl over 100 web pages per second using 4 crawlers at a peak speed of 600K per second of the data. Each crawler maintains its own DNS cache. The crawler uses the asynchronous input-output and number of queues. So this is a very simple structure: URL server, crawler, store server, repository, indexer, barrel, and sorter. So from URL server, data goes to store server and then repository, and then indexer indexes those data and store them into barrels, and then sorter sorts those entries. So first we go through the parsing. This is the starting or initial phase after crawling. So any parser which is designed to run the entire web must handle the huge array of possible errors. This may range of typos in HTML tags, kilobytes of zeros in the middle of the tag, non-ASCII characters, HTML tags, nested hundreds, dips, and a great variety of other errors and challenges. Anyone's imagination to come up with equally creative one. It uses the flags to generate the lexical analyzer for a maximum speed, and based on those techniques it identifies the words or it converts them into indexes and then store into barrel, and then sorter sorts it. So indexing the documents into barrel. After each document is parsed, it is encoded into number of barrels. Every word is converted into a word ID by using an in-memory hash table called the lexicon. New addition to the lexicon hash table are logged to a file. The words in the current documents are translated into hit lists. The words are written into the forward barrels. For a parallelization, the indexer writes to a log file. For parallelization, log file is necessary so that you can analyze that which barrels. The log file contains the information about the lower and upper limit of the sorted index stored in the barrel. So that's why a log file is maintained instead of sharing the lexicon. Takes each of the forward barrels. Now the sorting page takes each of the forward barrels entry, sort it by word ID to produce the inverted barrel, and then parallelize the sorting page. The parallel operation is compulsory. This is very helpful in reducing the sorting time. Subdivides the barrel into baskets to load into main memory because barrel does not fit into the main memory. Sorts the basket and write its content into the inverted barrel. Simple searching page. Parse the query, convert word into word IDs, seek to the start of the doc list in the sort barrel. For every word, scan through the doc list until there is a document that matches all the search terms. Compute the rank of the documents for the query. If we are in the sort barrels and at the end of any doc list, seek to start of the doc list in the full barrel for every word. Then we again go to the start of entire scanning. Go to the step 4, which contains the scanning and searching. If we are not at the end of any doc list, then go to step 4. Scan through doc list until there is a document that matches all the search terms. Sort the documents that have matched by the rank and return the top key. So this is simple Google query evaluation techniques. So this barrel contains the sorted indexes. When we use the query converted into IDs, and we search those IDs from barrels and then rank the documents based on their importance, based on the importance with respect to query. So now the ranking system. Every hit list includes position, font, capitalization information, factors in hits form, anchor text, and page rank of the document. Ranking function so that no particular factor can have too much influence. This is important part. For a single word search, in order to rank the document, Google looks at the document's hit list for a single word query and computes an IR score combined with page rank. I already discussed about page rank. So page rank, Google first of all calculates the page rank score of every document. It also uses the IR score, means similarity of the documents with given query, and documents hit list. It combines all three features to finally rank the documents. For multi-word search, hit occurring close together in the documents are weighted higher than hit occurring far apart. Here also Same strategy is applied, but hit occurring close together in a documents are weighted higher than hit occurring far apart. Means all multi-word search available in the same documents with minimum distance at minimum distance should get higher IR score, and then we combine, actually Google PageRank combine their PageRank score and documents hit list. Here hit list of the document in which all words come together get higher importance. Use of feedback. Google also uses the feedback in ranking. Google has a user feedback mechanism because figuring out the right value for many parameters are very difficult. When the ranking function is modified, the mechanism gives a developer some idea of how a change in the ranking function affects the search result. So Google search engine ranking system also use the user feedback to enhance the quality of ranking. Page rank. So this is a simple page rank formula. Page rank of any node shows how many important or popular nodes vote for a given node. This is a collective intelligence of nodes in a graph. For example, page rank of node Vi dash is equal to 1 minus lambda divided by n plus lambda into sum of rank of all incoming links. Here SVJ denotes the pages which are from which incoming. For example, suppose we have to rank the page A and incoming links are coming from page B and C. Both page had some outgoing links. Then after this part will be lambda m into page rank of B divided by number of outgoing links is equal to 3 plus page rank of node C divided by number of outgoing links. This will be the page rank of page A. So now here SVI dash is equal to rank of vertex VI, SVJ dash rank of vertex VJ dash from which incoming link comes to the word or vertex VI dash. N is equal to count of number of vertex in the graph. Here we considered the word graph because we considered word. In case of search engine ranking, we treat vertex as a URL address or page ID of the particular page. Damping factor, this part shows the probability with which random var will backtrack. This is the probability with which the control will jump to a particular page, and this part shows the rank due to the structure of the connectivity of the nodes. This is a simple architecture, Google architecture. Here the URL server crawler crawls the pages and store it as a store server. This is repository. From repositories it sends to indexer, indexers to anchorers. From anchorers the system identifies the URL addresses, and from URL addresses and indexes Both are stored to the barrels, and there is a sorter used to sort the entries in each barrel. Now, from indexers, we store information to lexicon also. So, indexer also stores document indexes. URL resolver also stores document indexes and links, and based on the links, document indexes and entries in the barrel, page rank is calculated, and searcher gives the final information based on the indexes matched in the documents, based on the lexicon, based on the document index and page rank. So URL server sends the list of URLs to be the fetched to the crawler. Store server compresses and stores the pages. Indexer extracts the words, their position, size, capital, etc. Anchors counts dot link and their text. Sorter generates the inverted index. Searcher uses the lexicon to and page rank. So this is a general description of Google PageRank architecture. Major data structures are: Google data structures are optimized so that the large documents collection can be crawled, indexed, and searched with little cost. Designed to avoid the disk seeks whenever possible, and this has had a considerable influence in the design of the data structure. First is big files. Big files are virtual files spanning multiple file systems and are addressable by 64-bit integers. Second is repository. The repository contains full HTML of every web page. Each web page is compressed into JLib by using JLib to zip format. The repository requires no other data structure to be used in order to access it. This helps the data consistency and make development much easier. Next is document index. The document index keeps the information about each document. It is a fixed width. Google uses a fixed width IASM, index sequential access mode, indexes ordered by document ID. The information stored in each entry includes the current document status, pointer into the repository, and a document checksum and various statistics. Includes the current document status, pointer into the repository, a document checksum, and various statistics. Additionally, there is a file in which is used to convert URL into document IDs. It is a list of URL checksum, which they are corresponding document IDs and sorted by checksum. In order to find the document ID of a particular URL, the URL checksum is computed and binary search is performed on the checksum file to find its document ID. Lexicon. This is lexicon. Document indexes, already discussed. It keeps the information about each document. Repository, full HTML of every web page. Next is lexicon. Contains 14 million words. Though some rare words were not added to the lexicon. It is implemented in two parts: a list of words concatenated together but separated by nulls, and a hash table of pointers. Next is hit lists. A hit list corresponds to a list of occurrences of a particular word in a particular document, including position, font, and capitalization information. Hit lists account for most of the space used in both the forward and inverted indexes. Forward indexes and inverted indexes. Forward index is actually already partially stored. It is stored in a number of barrels. We use this here in Google, use 64 barrels. Each barrel holds a range of word IDs. If a document contains words that fall into a particular barrel, document ID is recorded into barrel followed by a list of word IDs with a hit list which corresponds to those words. Hit list actually contains the information about that word, particular word, including font, capitalization information, position, related. These features can be used in ranking. These features can be used when we fire a query. Then these features can be used to rank the documents in addition to the page rank score and other features. Inverted index. The inverted index consists of same barrels as the forward index, except that they have been processed by the sorter. Every valid word ID, the lexicon contains pointer into the barrel that word ID fall into. Thanks. So these are the basic data structures used to support the complete Google architecture for page ranking. Thanks.